participants. Good morning, good afternoon. Thank you very much for joining us. And I'm so honored to be your host today, especially for the talk of my PhD supervisor. Today we have Professor Manuel Hernández-Pajares, who, because of his expertise, significant contribution, and impact in the field of GNSS Ionosphere, probably needs no introduction. I have known few intellectuals who are as busy as him, are as productive as he is. For the audience who are not from GNSS Ionosphere field, I will introduce his achievements as follows. And Manuel Hernández-Pajares was born in Barbel de Leganés, Badajoz, in Spain in 1962. He got his PhD in physics and astronomy in 1990 at the University of Barcelona. He's a full professor at UPC since 2010. Since 1994 until now, 3 decades, he has focused on GNSS ionosphere and precise navigation. He has been the chair and product coordinator of International GNSS Service, the Ionosphere Working Group, and the principal investigator of more than 50 scientific projects with a funding above 4 million euros, most of them in international projects, one in competitive calls. He has published 148 papers in peer-reviewed international journals, most of them in first quartile of impact factor. And he is the first author of 2 national and 3 international patents. His publications have received on December 2030 about 9,000 citations. He has been advisor and a co-advisor in 15 PhD thesis dissertation. He has been associate editor in IEE TJRS, Radio Science, Space Weather, and Journal of Geodesy, and expert advisor of the European Space Agency in the GNSS Scientific Advisory Group. He has co-organized the International Beacon Satellite Symposium meeting, and he has been invited lecturer in postgraduate international courses in USA, Germany, Argentina, Brazil, Pakistan, Italy, and Kenya. He created a new research group, UPC IONSAT, in 2013. In this webinar, he will summarize the main GNSS effects and computation of this distribution of free electrons located at the partially ionized part of the ionosphere above 15 kilometer height from GNSS multi-frequency measurements courses and its applications such as space weather monitoring, precise real-time positioning, and among others. That's so impressive achievements. Thank you, Manuel. Thank you very much for taking your time. And now you have the floor.
Thank you very much, Haisha. Thank you very much for your kind invitation. So the idea is, I try to do here something like I call visual introduction to GNSS Ionosphere, which I prefer in the last similar lectures I have done, because maybe it's easier for and it's more effective for, in particular, for the young people to be more or less to follow and to be more motivated. And so the first part will be the visual introduction to GNSS Ionosphere, and the most part of the talk will be this. And at the end, I will just provide a sample of some challenge, synergies, and applications of GNSS Ionosphere. In these works, there are many people involved. So I you will see some of the people at the end in some of the references regarding to the challenge applications and synergies. So what is this? This can be a question. What is this movie? What does this movie represent? Okay, so obviously there is a map, a low resolution map for the borders of the continents, but the overimpose this movie. What is this movie showing? So this movie is showing the animation of the vertically integrated electron number density that is called typically vertical total electron content, which is a number measured which takes into account the number of free electrons mostly in the upper part of the atmosphere and the ionosphere above, let's say, 50, 60, 70 kilometers height, up to 1,000 kilometers height and more and beyond, and per square meter, I mean per area unit. So this is, we can see this is during one day in 6 October 2023. And this was obtained thanks to the multi-frequency measurements of the global navigation satellite systems. Of course, you can access real time. These maps are computed in real time, and also the link is here, so it can be seen in this link what is the latest real-time GIM, if in case we want to do it. Why are these free electrons within the Earth atmosphere? Why we can find these free electrons? As it is well known, the chemical reactions interacting different neutral molecules with the ionizing solar photons, mostly UV and also X-ray bands, are the responsibles of the free electrons at different heights with different predominant equations at different heights. How can the BTEC distribution be explained? I mean, this BTEC distribution that we have seen before, how can be explained? It is well known, sorry. We can just take into account a simple model can explain the main characteristics, the solar irradiance, the different solar irradiance in function of the latitude and local time. And the local time is related with Earth rotation. So basically, it's very dependent on the solar zenith angle for the efficiency of the ionization, the energy per square meter of the sun, especially UV, and also of course the rotation. I mean, in the night side, there are much lower electron content that in the day side where the free electrons are being generated. But we can see two peaks here. Anything else to be explained? What about this double BTEC peak, that so-called equatorial anomaly? So this is explained thanks to the so-called EB drift, the drift generated by the electric field and magnetic field around the geomagnetic equator, which is a sort of elevator of the free electrons, which go up, that go up and fall to the both sides, generating a maxima instead on the equator, as it will be expected, around the equator at two sides of the equator, more or less plus minus 20 degrees of geomagnetic latitude. We are seeing all these things with GNSS data. So, and what is this? How can it be explained? I mean, that we have in this plot is the height at the y-axis above the ellipsoidal height, and in the horizontal axis, the electron density, the number of free electrons per cubic meter. So we can see that there is a peak, in this case, around 200, 300. And this peak, how can it be explained? So is a height where we have an optimal production of free electrons, enough target molecules to be ionized mostly by the UV photons from the sun, and enough UV radiation, not filtered out by the atmosphere, not too much filtered out by the atmosphere. So this has been estimated, this electron density profile for corresponding to this September 18 of the year 2011 was estimated thanks to the measurements from a low Earth orbiting, the GNSS measurements, GPS measurements from a low Earth orbiting, one cosmic LEO. Okay, so this is likely still also very well known. What is this? Any guess? Obviously, these are global navigation satellite system transmitters and an artistic representation of one receiver in supposed to be in an airplane here. What this layout represent? Okay, it's also very well known that this represent the trilateration concept. So if we're able to measure the distance versus one transmitter, we know that we are in a sphere around this transmitter with a radius of this pseudo range, this almost range measure from them. And if we have simultaneous measurements, we can get our position by intersecting these spheres. This is a simplification, of course, to interpret geometrically the problem, that we have many more terms here, but these are the main ones. So the pseudo range are computed correlating. These almost range are computed obtaining an apparent transmitting time, that is well known from GNSS. And this is done by correlating with a replica of the pseudo random noise code. And it is well known that there are several error sources affecting the pseudo ranges. And these measurements obtained by this apparent time delay tau measured from the delay in the correlation of the incoming signal with the replica at the receiver multiplied by the light speed in the vacuum provides the pseudo range. But very interesting, the curve phase is very interesting because it's much more precise than the pseudo range. It's less accurate, but much more precise. And the curve phase, as it is well known, is obtained by integrating let's say, the drift of the frequency of the received signal. We can say the Doppler term, integrated. And this is, in fact, the most useful observation for GNSS Ionosphere, the carrier phase. Also, this plot can be used to generate some discussion. What is this? So it is indicated here. The blue points corresponds to code measurements. In fact, the difference of code measurements, simultaneous code measurements of the same transmitter, the same satellite, GPS PRN-01, from the same receiver, is not indicated here, the receiver, sorry for that. And these are the blue points. The pseudo range can be noisy. We have removed all the geometric dependencies, and mostly the variation is mostly due to the variation of the electron content along the line of sight of the observations. So it can be seen in the blue points is quite noisy, but continuous. But the red points corresponds to the carrier phase. Similarly, the difference between the same frequencies with a change of sign due to a different dependence on the ionospheric term that I am going to show in the next slides. And you can see it's very, very clean, very small noise compared with the pseudo range, but we can find a jump here. We have lost the lock. The term is here. The reason of losing the lock is, let me to come back to the way in which the carrier phase is measured. We say that we commented that we integrated the Doppler term. So this means that we have an initial value of the carrier phase at the locking time. So if the lock is lost, so we have a new locking time, and we have a new initial term that we call ambiguity. So there is a jump in the measurement. So we have to detect the very well-known problem of detecting cycle sleep to estimate the ambiguity, the new ambiguity. But it's very, very precise. And this here you can see the different sign in the dependence on the ionospheric delay. So this is the reason why the combinations are the order changed in order to provide always the dependence in terms of a positive term depending on the integrated electron density along the right path, line of sight, S slant EC, it's called slant EC, multiplied by a physical constant in international system units and divided by the square of the frequency of the signal. This is demonstrated from first principles, the Apperton-Hartree equations. Okay, the other terms are the distance, clock errors, tropospheric delay, instrumental delays, wind up. So, but these are the main ones for us, for GNSS Ionosphere. Okay, so this is the way to isolate, as I showed before, difference of carrier phases, L1 minus L2, P2 minus P1. We cancel out the other terms and we focus on the slant EC and other terms which are small or constant, like the ambiguity. Okay. So like we can conclude at this point of the presentation, we can say that the GNSS Ionosphere is well data supported. Why? Because we have presently more than 100 transmitters, GNSS transmitters, mostly medium Earth orbiters, but also some geostationary and geosynchronous, like those from Beidou, for instance, and more than thousands, in fact, of permanent receivers working 24/7, static receivers, and providing the data, many of them openly, like in the case of the International GNSS Service, and hundreds of them are providing the data in real time in data streams, like using similar protocol than the internet radio stations. When you are traveling, I like to follow my radio station here in Barcelona, and when I travel, I used to follow it through internet. Maybe you are doing similar, or TV or other. So similar protocol is used for broadcasting the data, and you can get the measurements from any receiver worldwide, from Arctic to Antarctica, in less than 2 seconds. So it's very impressive, works very well. So in this way, GNSS becomes an scanner of the ionosphere. And this can be a very good input for the global ionospheric maps that we have shown at the beginning, summarizing the big GNSS data and other ways of modeling and studying the ionosphere. So this brings this definition, we can say, of the GNSS ionosphere that could be defined like effects and computation of the distribution of free electrons located at the partially ionized part of the atmosphere above 50 kilometers height from the global navigation satellite system measurements, usually multi-frequency, but not only. You can also single frequency, you can work. Let me just to clarify this, because thanks to the different sign in the dependence on the ionospheric delay from the pseudo range and from the carrier phase. So subtracting both pseudo range minus carrier phase of any given frequency, you get 2 times the ionospheric delay that you have affecting, for instance, the pseudo range or the carry phase, but it's very noisy due to the problems of the pseudo range. But at low latitude, it can provide an advantage because it has been demonstrated in recent works led by colleagues from Brazil, like Fabricio dos Santos Prol and other colleagues, that working in one frequency, in the frequency less affected by scintillation, this can be an advantage. But this is another particular point. Yeah, but in general, usually multi-frequency is the best scenario to be able to work with the carry phase with more clean measurements and much more precise. So this definition of these multi-frequency signals, which are crossing the ionosphere, these multi-frequency GNSS signals, and its applications such as space weather monitoring, precise real-time positioning, and in general, precise geodetic modeling, among others, can be defined like GNSS Ionosphere, and is very well data supported, as we have just commented. Okay, I selected here, let's say, 10 challenges or applications and synergies of GNSS Ionosphere, just to comment briefly. The first one is a challenge because it's not an easy problem, is relating the relationship between SLAN and vertical total electron content. Previously, we have shown in this visual introduction to GNSS Ionosphere, we have shown that we have shown some global ionospheric maps of vertical total electron content that were computed from SLAN observations, typically observations from transmitters, medium Earth orbiter transmitters to receivers, which are typically slant. So the relationship between SLAN and vertical in the two ways, first to build up to estimate the global ionospheric maps, and secondly, once the user receives a global ionospheric maps, to apply it to the given line of sight, you need the so-called ionospheric mapping function, which relates the slant and vertical total electron content values. So there is a typical mapping function assuming thin layer models, assuming that all the electron content is concentrated at a fixed height. This is not bad, but can be improved, because this is just like assuming that the electron density profile that we showed before collapse and in a thin layer. But also this height that we commented before, where we have the highest production of free electrons because we have enough number of neutral target molecules and enough ionizing UV radiation. This height can change significantly, and in low latitude, for instance, you get much higher heights with the peak of the ionization. So assuming a thin layer is not real, and assuming a constant value, but the thin layer height is not real. So this, for instance, this was one work led by Haisha Liu, Dr. Haisha Liu, that introducing an approach taking profit of the tomography runs done for many years at UPC for generating the GIM. So these tomographic runs, these low resolution tomographic runs, provided a very good database to be able to apply a height variant mapping function, more realistic. First, in this work for mid latitudes. Yeah. So this is one of the challenges among other challenges of GNSS Ionosphere. Another one, which is very now has been motivated in particular in Europe, by some agencies like EUMETSAT for exploiting the satellites for standard weather prediction. So they have become interested on the ionosphere as well, because for not neglecting the gradients and the variability of the ionospheric electron content, introduce a significant error in the height, in particular in the location of the measurements of the neutral refractivity profiles for weather applications from radio occultation. So they become interested on ionospheric radio occultation, and they have started to extend the height of the measurements, the so-called impact factor, the height where the observation in radio occultations, where the receiver is observing below the local horizon at the low Earth orbiting satellite. So for neutral atmosphere, this typically ends below 100 kilometers very clearly, because at these heights there are almost no, a very low density of neutral molecules. So, but they have extended the measurements of the satellites, of some the METOP satellites in particular, for hundreds up to 600 kilometers. These satellites were flying at and are flying at around 800. They extended up to 600 for during 1.5 months of campaign, and the EUMETSAT is going to launch replacement satellites in 2025, and the expected maximum height of measurement for the radio occultations will be 500 kilometers. 500 or 550 is not still decided, and this is much below the height of the receiver, which is will be flying around 800 kilometers. So these are the so-called truncated radio occultations, because we don't have the complete measurements series. Or for instance, if we have a satellite, a GNSS transmitter, which is seen in a setting radio occultation, so it's seen from the LEO going down from positive 0 elevation, negative up to more or less minus 20, 22, 20 something degrees regarding the local horizon. So it's very important to have the full data set, the full time series of the occultation to get an accurate electron density profile. But this is not possible if you are focused on the neutral radio occultations. You will lose neutral radio occultations at the bottom part, because your hardware should have to pay too much attention to the ionospheric radio occultation when the full radio occultation, ionospheric radio occultation measurement is done. So the solution is to truncate, to say, let's not measure the full radio occultation, the full ionospheric. Let's start measuring 500 kilometers of impact parameter height and below. And this is good for not losing neutral radio occultations from the hardware point of view, but is a very strong challenge for the ionospheric modelers. So in this work was provided a very good solution for this problem in Liu et al. in this paper in 2019, I guess. Okay, so this is another example of challenge. And we can talk about synergies. This is a very recent synergy from 2023 with the radio astronomy, measurements of pulsars in radio astronomy. This refers not to the first order. When we talk before ionospheric delay, we were actually referring to first order ionospheric delay term, this approximation that we commented, proportional to the slant EC, inversely proportional to the square of the frequency. This approximation is excellent for L1, for around the frequencies of GNSS observations, let's say between 1 and 2 gigahertz, for instance. This is an excellent, this approximation is accurate, typically better, more accurate than 99.9%. But if you are going down to with frequencies which are lower, this approximation, I mean, you need to take into account higher order terms. So the next higher order terms, the second order terms, which is the so-called Faraday rotation, because it depends on the integral of the magnetic field projected along the line of sight and the electron density integrated along the line of sight, and is inversely proportional to the cubic, to the third power of the frequency, and produce a polarization change, the plane of polarization of the signal. In other words, this is a signal which is affecting the radioastronomical measurements of the pulsars, and this synergy has been very nice because taking into account these measurements, we have been able to compare the efficiency removing this effect from the Earth ionosphere, because there are other similar effects, but for the interplanetary interstellar media. But they were interested, of course, the colleagues, the radio astronomers, to remove the footprint of the ionosphere, and they were able, we were able in this collaboration to compare the quality of different ways of modeling the ionospheric delay for the second order, for the Faraday rotation term, and providing, in other words, we were able to use radio astronomy pulsar measurements to assess the GNSS Ionosphere product, the global ionospheric maps. So yeah, this is another one recent challenge. Okay, applications. This is a very recent application. In fact, this is from this year, was published maybe 1 week ago, to use GNSS Ionosphere, in particular, the global electron content, which is the total number of free electrons. Remember, vertical total electron content refers to the vertically integrated electron density, which provide in you can imagine a cylinder, a column of vertical column of 1 square meter of base, I mean of section. You project this vertical column up to the GNSS satellite orbit, typically around 20,000 kilometers height, and the total number of free electrons, this provides you the VTEC in this cylinder of section of 1 square meter. But you can integrate all these electrons that you have in these cylinders, let's say, you can integrate to the whole ionosphere and you get the total number of free electrons. It's called global electron content. It was introduced by Professor Afraimovich more than 2 decades ago. And we have demonstrated recently in this collaborative work led by Dr. Aroca Ferrerons, that the global electron content, the spectrum of the global electron content can work very well like a space weather activity indicator. Yeah. Another application, as well as in the same way in the new potential indicator, is to compute a ionospheric storm scale, which is from the global ionospheric maps to compute the relative variation of the VTEC compared with the previous solar rotation, previous 27 days, using medians for the given pixel. So for every pixel, for every one of these more than 5,000 pixels which compose a typical global ionospheric maps, as following the resolution that is used in IGS, in the International GNSS Service, 5 degrees in longitude by 2.7 degrees in latitude, and in time can be 1 hour, 2 hours, or 15 minutes, depending on the regime. So for every pixel, you can compute this relative variation of VTEC regarding in the latest 27 days, and standardize minus the mean and divided by the standard deviation for similar season conditions and the same pixel, similar local times, in computed during several years of reference up to 2014. So this produced an index, ionospheric storm scale index at every pixel of the GIM, which works very well as well as a local or regional space weather indicator. Applications of GNSS Ionosphere also we can characterize rapid ionospheric fluctuations. This is also a very recent paper showing with GNSS Ionosphere the power law distribution of the fluctuations of the free electrons, rapid fluctuations. Another example of these 10 selected examples, recent examples as well, are the applications. We can go as well to applications. Low Earth orbiting based ionospheric tomography, using only data from receivers on board low Earth orbiting, flying at, let's say, 700, 800 kilometers, for instance. We have shown that we can perform ionospheric tomography, quite accurate, and also an accurate estimation of the transmitter instrumental delays affecting the pseudo ranges. Another application is the precise positioning. The ionospheric model coming from GNSS measurements provides a fast and far away, let's say, approach for this precise positioning. Allows, in other words, to get a precise position convergence time much shorter, and also to work much farther away from permanent receivers, for instance, in wide area approaches, instead of local or real-time kinematic approaches. And the applications, of course, for agriculture is very clear. Another application which is of interest is for tsunami detection and potential warnings, because I mean the atmospheric gravity wave generated by a tsunami moves upwards in the ionosphere and can be seen farther away due to the high height, effective heights of the ionosphere, hundreds of kilometers, and there's so many GNSS measurements. So it can be seen farther away and also globally in real time. And we have shown that either with data from LEO, from receivers on board a low Earth orbiting with antennas, not from radio occultation, but either just pointing towards the zenith for precise orbit determination, we have been able to detect potential tsunami signatures. And this makes the usage of constellations of LEOs one potential important application, provide warnings of this kind of natural hazard events. Okay, and this is another application that is working during, as it is said in the title of this recent paper from 2023, running during more than one solar cycle, that we call GNSS solar astronomy. With these signals, using a simple overionization model, we are able to estimate the UV solar flux rate. We can estimate. In other words, we can convert the ionosphere, the sun-illuminated part of the ionosphere, in a giant sensor, in a giant GNSS solar astronomy instrument, and we have shown in different publications that the correlation with direct measurements of UV flux rate is very, very important, very, very high, and also with constants which are, with factors which are constants like it should be. The factors are given by physical constants in this simple but quite accurate overionization model, taking profit of the fast phenomena. The solar flares used to be very fast events. So this allows to neglect magnetic field transport as it is done in astronomy and astrophysics, for instance, for other problems, and it works very well. And we are providing this in real time for almost one solar cycle. This is one product that we produce. Warnings of solar flares and also estimations of the UV flux rate from the sun. And okay, we can come back to the conclusion that the GNSS, we can enforce the previous conclusion that the GNSS Ionosphere is well data supported. And that's all. Thank you very much for your attention.
Thank you. Thanks very much for this fruitful publications and sharing the knowledge with the audience. Anyone who has questions, please feel free to, unmute yourself or write something in the chat. Shukri, I see you are here.
Hi.
Yeah. Hi. Yeah.
Okay. Thank you for the presentation. Actually, I have a question. As we know that the GPS currently have the triple frequency, so can you comment on the uses of the triple frequency in minimizing the ionosphere by minimizing the ionosphere errors in the GPS measurement?
Yes. Yes. Yes, I mean, the triple frequency, for instance, one maybe is not exactly your question, but one of the first targets or first potential benefits of the triple frequency measurements was for ambiguity fixing. I have not mentioned almost nothing about carrier phase positioning based on carrier phase, but as it is well known, or I mean, in case you are working on this area, in order to get the maximum accuracy in the positioning, you need to use carrier phase data, and also, especially if you fix the ambiguities, you estimate these ambiguities, but fix it in double differences between transmitters and receivers to the entire value in cycles is when you get a maximum accuracy. So for this process of ambiguity fixing, this is related with this application that I have just commented, weight area, for instance, GNSS corrections for precise positioning. So when you're working with two frequencies and with the ionospheric model, you can fix ambiguities better, and this is the key to get faster, precise positioning, and also to be able to do it far away due to the, in case you are using a good model, ionospheric model with very realistic. But if you have three frequencies, the process of ambiguity fixing is much more faster. It's not so dependent on the ionospheric delay. So on the one hand, for positioning, the triple frequency is very convenient for speeding up and improving the ambiguity fixing process, because you can start not by the so-called wide lane. You have an extra wide lane that, in other words, with the pseudo range, you can start fixing one combination of ambiguities of the three carriers involved, and this opens the door to facilitate the ambiguity fixing. From the point of view of the GNSS Ionosphere, the three frequencies, simultaneous measurements in three frequencies, in principle, will allow you for a better, I mean, to deal with the higher order ionospheric terms in a better way. In principle, you can consider the second order term, which is which appears with inversely proportional to the cubic value of the frequency, and you could mitigate or higher order dependencies. But in the practice, in my experience, the frequencies are too close for obtaining a reasonable value. The value is not very good, but yeah, this might be another application. Yeah.
Okay, thank you.
Welcome.
Yeah, Professor Daya Shankar. Yeah, please.
Yes, thank you. Thank you, Professor Manuel. Very nice and comprehensive presentation.
Thank you.
I just wanted a query. You have, although shown the published paper for the detection of the tsunami by using this GNSS data. So could it possible that the concentration of electron density in the ionosphere could give some indication about the impending earthquake?
Sorry, can you repeat the last question? I have follow you, but I have some problems. Let me increase the level of my micro.
Okay, no problem. I am
The
repeating.
question, please, if you can repeat the question. Yes.
Could it possible to detect the impending earthquake by the concentration of electron density in the ionosphere?
Yes. We let me yes. We also, it's another application that I didn't show you. Not only the tsunami, the earthquake is still more clear and more. It can be detected from the ground very clearly. The acoustic waves. The impact of the acoustic waves, and later on also the in case there is a tsunami, the atmospheric gravity waves. So this is very clear, and also this is an important application that there are agencies like they are implementing. I mean, GPL, NASA, for instance, in my knowledge, also the INGP in Paris, they are setting up systems to follow, to detect this kind of ionospheric signatures, and also to be able to monitor the earthquake impact on the ionosphere.
Very nice answer, but I have some doubt that earthquake focus is 30 or 40 kilometer below the subsurface, right? So how the energy or what interaction will take place to the atmosphere to increase the concentration of the electron? What phenomena passes?
Yes, you can imagine. I mean, these waves in the earthquake, these waves are transmitted to the air, and in principle, this, for instance, let's think in these oscillations of the air. At the beginning, at low heights are small, but when the signal is going up, the density of the atmosphere is decreasing, and by conservation of the energy per volume unit, the amplitude increase. I mean, when the good thing is that when the signal goes up, the amplitude increase by energy conservation, right? Because the energy per volume unit should be approximately the same, and as the density goes down, this means that the amplitude needs to increase to maintain the energy. So this is the good thing. When the signal arrives to the height of the ionosphere, a few hundred kilometers height, the amplitude is very high, and this moves the free electrons as well. And this wave, these oscillations are very clearly seen with crossing observations from GNSS with line of sights. And in fact, this is something that can be. Sorry, let me very quickly show you another paper. It was not selected, but another paper. For instance, here, let me show you. Let me show you. Yeah. Let me bring this to you very quickly. You can see an alternative tool for studying earthquake tsunami signatures in the ionosphere. So this was a very large, you can know it, the Tohoku, right? The Tohoku, which produced the disaster of the Fukushima atomic plant in Japan. So just to show you some the signatures from the ground, the network of stations, the signature. You can get, for instance, this is very useful, the so-called chaograms. You can compare the signals of so many, the trended values of the ionospheric delay from the GNSS signals versus the distance, and you can get very clear propagation patterns, and also you can estimate the velocity. And also you can see here, maybe I can make larger, you can see here the footprint, the horizontal footprint, all from observations, from GNSS observations without any models, very clear waves. So this, of course, this was a very extreme earthquake, but this can be seen as well for much smaller earthquakes. Yeah, and this is the secret, let's say, is the energy, the conservation of the energy per volume unit, which makes large oscillations, produce large oscillations when we have free electrons. So this is the opportunity, let's say, this is the reason why it affects can be detected quite clearly. Yeah, from GNSS.
Yeah, thank you. Very nice explanation and very nice publications. But my observation is when the seismic wave generated at the focus and encounter to the surface of the earth, how it can go beyond the surface, because there is a free surface and seismic wave doesn't travel in the free surface.
Do you mean the travel of the
Seismic wave?
Yes, I mean is for instance is it's like I mean the lithosphere oscillates like following the acoustic, for instance, the acoustic waves.
Yes,
And
yes.
this oscillation is transmitted to the atmosphere. So this oscillation goes up, and as I commented you, the lower the decreasing density makes that this amplitude increase in size and affects the free electrons at few hundred kilometers. So it is detected through the GNSS crossing signals. It's after the earthquake. I'm talking always when the earthquake is happening. I'm not talking before. I'm talking.
Okay. Yeah. But our problem is we wanted to before this earthquake, some signal.
Yeah. This is not, I mean, this is more polemics.
Okay.
Yes, I know. And I have had some collaborations on that. I mean, it's not, it's more, I mean, there are models which, and also, I mean, serious works from different groups in Russia, in Japan, showing, also providing the physics about how this is produced, and also observations, in particular in Japan, with taking profit of this very high number of stations that you can see here from the observations in Japan. So but I admit that it's not, maybe not so easy to explain. Yeah.
Thank you so much.
Welcome.
Thank you. Very nice presentation.
Oh, very welcome.
Anyone has questions? We have a question from Dr. Bruno in the chat, Manuel. You can, you can select one or two to answer them.
Let me see. Okay. Yeah, I see. Is from, okay, Professor Bruno. Okay, I see. Questions I am reading from Bruno Chiamulesire. Sorry. I have some challenge in understanding how the second and third order parts of the sphere are modeled completely. Please share some details on that. Okay, so let's go. Let's go. Let's go. Okay. Is higher. Okay. So, okay, there are, I mean, maybe the more detailed place, at least in geodetic, for geodesy, for space geodesy, is to look at the Earth rotation rotation service documentation. But okay, in this paper, for instance, it's summarized the different higher order ionospheric terms. So just to not explain, to not enter into many details, just to tell that there are, this is, let me make larger. Yeah, the first order is depending, is with inversely proportional to the square of the frequency, and is proportional to this slant EC. This is the one that the 99.9% of the effect for GNSS measurements. But second order, I mentioned before, is the integral of the projection of the magnetic field along the line of sight multiplied by the electron density and integrated. This is the second order, and is depending f2 minus 3. Maybe I can show you an equation more compact. Let me see if I have a more compact equations below. Okay, anyway, let's come back to the table to not waste your time. Let's come back to the table. What's here? Okay, and we have third order terms. We have two third order terms depending f2 minus 4, and this, we have these two terms, and that depends on the square of the electron density, and also this product with the square of the electron density of the magnetic field. Typically, the second, this second term, third order term, is much smaller than the first one. So typically this is enough. And also, but these are assuming strain propagation, but also we have the geometric bending, the actual propagation is not in a straight line. So there is a bending due to the refraction. And then you need models, empirical models, or semi-empirical models for dealing with the bending, with the geometric bending and the D-step bending. The D-step bending is because the bending also is a bit different between the two signals. When we combine, as we mentioned before, carrier phases in particular into frequencies, we subtract them. The two ways are almost the same, but not exactly the same due to the different bending, because the frequencies are as different, slightly different. So the way is a bit different. So the slant EC along these slightly different ways can be a bit different, especially when there are strong gradients. So this is another effect, the D-step bending. So we have this basically the first order, the second order, the two terms, mostly one for third order that I have just mentioned, the one emphasized here, the geometric bending and the D-step bending that should be taken into account. So in this, if you are interested, for instance, the impact on the mitigation, this is one paper that we were working some years ago. Is from I can copy in the chat. Let me copy in the chat and yeah, the reference. Okay, this is regarding the point number 1. Point number 2. In case of a triple frequency GNSS receiver, how is the equatorial anomaly? Sorry, I don't see it. Anomaly handle any handle the equatorial anomaly. Any reservoir, I will glad to receive them. I mean, in my view, in my experience, if we are thinking, it's different if we are pointing to to ambiguity fixing for making faster the precise positioning convergence. But if we are focusing on GNSS Ionosphere for ionospheric determination, one way is to set up all the frequencies we have without combination in an uncombined way. Of course, the effort of modeling is larger, but in an uncombined way, you don't need to think what combination should I have. You don't need to wait to think about the correlations because you are using combinations and you can repeat one of the two carriers in other equations. So in other words, my suggestion will be to add the simultaneous observations in different frequencies as additional equations in the overall model with the geometry part and the ionospheric part. And in this way, you can isolate and you can estimate in a very convenient way the ionospheric delay. You need more effort for the modeling, of course, but it's very convenient for the so many different frequencies, many different systems, GNSS systems to deal with. And point number 3, yeah, I have one. There is one paper on that. I can try to provide you you asked for a reference. Let me to provide this reference very quickly in the chat because you asked about the uncombined approach. Let me to copy the reference for the uncombined approach. Let me one here. Is this where is this? Where is the reference? The reference will be in some place. Okay, let me go to the end. Otherwise, I can send the title and you can find it. Or I can, of course, I can send you the paper, of course, if you are acknowledgements. Okay, so if you can tell me and I can send you the paper, but I send you, this is one example of modeling. This is for precise positioning, but you can see the model. Yeah, it's here. Okay, it's here, the reference, sorry, it was here. This one, and this one. No. Okay, this is point number, you have the reference. Number 2, I have looked at some studies where one GNSS station is used to study the ionosphere. How effective is it over a large area in low latitudes? Aha, good question. Okay, it depends what do you want to do. For instance, with one receiver that you can do, for instance, if you consider GPS transmitters, MEOs, satellites, as you know, they have there is a repetibility period of the line of sight of one sidereal day. After one sidereal day, the receiver turns once, the permanent receivers, one rotation of the Earth and 2 orbits of the satellite. So you get the same geometry. So one thing that can be done, this is a very old paper. I mean, I can provide you the reference, but it's from 97. You can use, with one single receiver, you can track very well and very accurately the variations of the electron content, taking differences regarding the previous day, for instance, using the same geometry. This is very good because this allows to mitigate or to reduce the multipath, because as the line of sight is the same, when you consider the pseudo range, the multipath cancel out in the difference because the multipath depends mostly on the geometry, unless there is a rain and the surface properties can change due to heavy rain or whatever. But in general, it's very repeatable, the multipath, when you repeat the same line of sight observation. So I guess this is an old, sorry for that, it's a very old, but it still works. I'm applying this technique for another studies of GNSS astronomy. During these days, I have been applying this technique. Let me give you it's a letter, an old letter from Gerald. So this is, I suggest this is so old that is not, it was a scan. the PDF is not, I cannot copy and paste, but I can provide the reference GRL volume 24, number 13, pages 46, July 190s. So, for instance, this is one possibility. It's not the only one, but this is quite also at low latitude. This can give you a very good and accurate variability of the slant TC variation, and also the VTEC with the problem of the mapping, of course. Okay, fourth question. Any examples of the effects of using different antennas to study the ionosphere? Aha. Yes. I have another example, recent example. I mean, the different antennas, we can discuss at different levels, but in general, I mean, I have not found a significant difference between geodetic antennas. I mean, I cannot tell you, I found this antenna which is much better than this one. No, the geodetic antennas are quite, in general, at least for the GNSS Ionosphere, are very, in general, quite valid. It's different, of course, if you are thinking on a GNSS, on a smartphone. So the smartphones, a big problem among others, but among the duty cycle, but a big problem is the antenna. This is a strong limitation for the measurements. But now there are low-cost receivers which provides also a good antenna good enough for GNSS measurements. The problem, I mean, the point for the antenna is not, don't forget my small advice, suggestion, don't forget to properly apply the phase center variation, phase center offset correction, because otherwise this can be felt, for instance, in the DCB that you are estimating. If you are estimating DCB, and this affects, is not important typically when you consider the dual frequency combination, ionospheric combination, but this can affect a little bit to, not too much, but a little bit to the accuracy of your DC estimation. But in general, if you are using geodetic receivers, at least in my experience, I have not found important differences. Maybe because I am most focused on carrier phase, and because in our approaches, we are not using almost pseudo ranges for ionospheric modeling. We are only using carrier phase. I have to tell you that if you are using carrier phase, then the antennas can be more important. If you are using choke ring, for instance, for protecting against multipath, you can get you can buy antennas with better multipath mitigation, and this could be felt, but it's not. This can be avoided. Let's say if you are processing mostly based on carrier phase, or you are using an elevation mask large enough. Yeah. I guess this was the question number 4, and I guess I don't see more questions in the chat. Maybe I'm wrong. Okay.
Yeah, I don't see. Yeah.
You are welcome, Bruno.
Okay. I think we run out the time. So really appreciate your time and the talk and answering the questions. And so Happy New Year. And
Thank you.
I wish everyone can have a productive 2024.
Yes,
so I think we can, So
Thank you.
Thank you.
Yeah.
So all the best.
Yeah.
Have a nice year.
Yeah. Let's stop here.
Okay. All the best.
You.
Bye. See you.
Bye.
Bye.
Thank you.
Bye.
Bye-bye.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.